Alright guys, in this section we're going to be discussing antiderivatives and indefinite integration. Up to this point in the course, we have been talking about the derivative. We have been deriving and studying methods and rules of differentiation. But now we're going to start thinking about the opposite process, the inverse process of differentiation. And we're going to start by looking at what the antiderivative is, and then we'll make the connection with what we'll later define as the integral. First, we're going to start with the definition of the antiderivative. A function f, capital F, is an antiderivative of lowercase f on an interval I when the derivative of capital F of x is equal to lowercase f of x for all x in that interval I. Okay, this is pretty straightforward. We're going to try to come up with a function, in this case it's the capital F for us, so that the derivative of such function is equal to the given function, lowercase f. Okay, so we're reversing the process here. We're trying to find a function whose derivative is equal to the given function. Okay, let's take a look at an example here. So if we're giving a function f of x equal to 2x, what function will give us a derivative of 2x? So one possible antiderivative for this function f of x would be x squared. Why? Because if you take the derivative of this capital F, it will be equal to 2x, which is equal to our lowercase f of x, right? So then, by definition, this function capital F would be an antiderivative to our lowercase f function. All right. In the same way, I can come up with a different function or another function whose derivative is also 2 of x. So think about x squared plus 1. So if you take the derivative of x squared plus 1, that would also give you 2x. All right, and then I can keep going, and I can also do x squared plus 5. And this will be another function whose derivative is also 2. So soon enough, you realize a pattern here that no matter what constant I add to my x squared, I'm always going to get the derivative to be equal to 2x, since the derivative of a constant is 0. So I can generalize this antiderivative and give a general antiderivative here, f of x equal to x squared plus c for some constant c. Okay, so the antiderivative is not unique, but instead this general antiderivative gives us a family of functions here at work. From this previous example, we can kind of build our intuition, sort of understand this next theorem as a representation of antiderivatives. If f is an antiderivative of lowercase f on an interval I, then g is an antiderivative of f on an interval I if and only if g is of the form g of x is equal to f of x plus c for all x in the interval I, where c is a constant. So if you have two functions that are antiderivatives of a given function, then they're only going to differ by a constant. So you can represent the family of all antiderivatives for this function 2x by this capital G of x equal to x squared plus c. Now we call this a family of antiderivatives because c can take the place of any constant. So if you think about your transformations from your algebra course, all that c is doing is shifting the x squared function up and down depending on what sign c has. If it's positive, it's going to shift it up. If it's negative, it's going to shift it down. It's a vertical shift. Okay, this c is going to be called the constant of integration. And the family of functions represented by this function g, capital G, is the general antiderivative of f as we were discussing. And this g of x equal to x squared plus c is the general solution of the differential equation g prime of x equal to 2x. This particular equation with the derivative is a differential equation, and a differential equation in x and y is just an equation that involves the variable x, the independent variable, the dependent variable y, and the derivatives of y. So we're just going to define what it is here so that we can understand that when solving a differential equation of this form, dy dx equal to some function of x, when we cross multiply, it's just going to be convenient to write it in the differential form dy equals f of x dx. The operation of finding all solutions of this equation is called antidifferentiation or the indefinite integration. So we're going to see that those two things are going to be the same, and it's going to be denoted by this symbol here for the integral, as we'll see. It will conclude later that the antiderivative is in fact the indefinite integral of a function. The antiderivative of a function is going to be equivalent to the indefinite integral of that function. Okay, so here is some notation for the integral. We have that the general solution is denoted by this y equals the integral of f of x dx, and that's equal to f of x, capital F of x plus c. Now, what's inside the integral is called the integrand. Then we have the variable of integration. Dx tells us that we're integrating with respect of x, just like we did for differentiation. And then we have the constant of integration is the c, and the antiderivative of lowercase f of x is going to be this capital F of x. Right? So this expression, the integral of f of x dx, is read as the antiderivative of f with respect of x. So the indefinite integral is going to be the same thing as the antiderivative, plus c for the family, all of those. So the general antiderivative of the function. All right, so here we have the integral of this capital F prime of x dx is equal to f of x plus c. With this, we show that integration is the inverse of differentiation and vice versa. The differentiation is the inverse of integration. So these are the two operations, and they do undo each other. Again, we've been talking about differentiation this whole time, and now we're introducing an opposite, an inverse operation to differentiation, and we call that integration, right? We represent the integral here with this symbol here. So if we were to take the derivative with respect to x of the integral of f of x dx, that should give you f of x, because the integral with the derivative with respect to the same variable, they cancel each other out, they undo each other, so you get that function back. All right, so now that we understand the process, understand what we're doing here, we're going backwards here of what we did when we on differentiation. We're gonna take all our differentiation rules or all our formulas and kind of go the other way now to come up with integration formulas. So notice how, remember that the derivative of a constant is equal to 0, so now the integral of 0 would be a constant, right? Derivative of multiple times x is equal to that multiple, in this case k. Then we can go backwards now. The integral of that k is going to be kx plus c. And remember, all of those integrals, the indefinite integrals, are going to have a c at the end of the solution, because we're really getting a family of functions. And then we also have the addition ones, subtraction, and then our power rule here at the end, right? We're going to undo that process as well. So we had our rule for power rule. We have the derivative of a power. Now we have the integral, right, of a power function there. We're going to have a nice rule there that's going to work for any n except -1. We can't divide by 0. So that's one that we're going to use a lot. The integral of x to the n is equal to x to the n plus 1 over n plus 1 plus c, of course. All right, and then we have more basic integration rules from our basic differentiation formulas. So if you remember all our trig differentiation rules for trig functions, we had the derivative of sine is cosine, the derivative of cosine is negative sine, and so forth. Now we can do the integrals of those and then get back the function, right? So we're just undoing the process of differentiation. So right now all we're doing is we're undoing all those derivatives that we found from our basic differentiation rules. We're building our basic integration rules from those. And remember, they all have a c at the end because it's really a family of functions. The antiderivative is not unique. So we have a whole family of functions there, represented as the integral of the given function. So notice how we have also derivative. We don't have integral of tangent, but we can do the integral of secant square is equal to tangent of x plus c, and so forth, right? Later on in a higher level calculus, or when you go to the next calculus class, you'll see how to do the other ones once you develop more integration techniques. The same way we don't have the integral of cotangent or cosecant or secant, but we have the integrals of all those derivatives that we found in our differential calculus. Okay, here we have a couple more rules. Our exponential functions, including the e to the x. And remember, e to the x was an easy one. It was itself, so the integral of e to the x is also e to the x plus c. And then we have exponential functions with a different base other than e. And then the derivative of ln x was 1 over x, so then the integral of 1 over x is going to be the natural log of x plus c. And we put the absolute value on the x just to make sure that it's a non-negative number and so that it can be defined. And that's why the power rule for integrals didn't work for when n was equal to -1, because we have that the integral of 1 over x is equal to ln of x. Okay, so here we have an example to start using our integration rules. We have the integral of x to the 5th power plus 1 with respect of x, and we have a sum here. This is a polynomial, so we can use our rule of addition rule, which says I can split the integral and find the integral of each term individually. So we have the integral of x to the 5th power dx plus the integral of 1 dx. Okay, and then look at each integral individually and apply my rules here. We have power rule. So we have that the integral of x to the 5th power is equal to, by the rule, is x to the 5 plus 1 over 5 plus 1, which is going to be 6, plus just 1x. And then don't forget to add your c at the end. So finally we simplified and we get x to the 6th power over 6 plus x plus c. Now remember, if you want to verify that this is actually the integral, the correct integral, then just take the derivative of this answer and see if you get the integrand, which was x to the 5th power plus 1. And you do. When you take the derivative of x to the 6th power over 6 plus x plus c, you do in fact get the integrand. Okay, here we have another example. Before we can do the integral, we have a binomial square, so we're going to go ahead and expand that so that we can take find the integral of each term. We can do it in the form that is given, since we have a whole polynomial being squared. We need to expand, distribute that first. All right, once we do that, we get the integral of 16x to the 4th power plus 24x squared plus 9, all of that with respect of x. And just like we did on the previous example, we're going to split the integral and just take the integral of each term individually. And notice how most of these terms have a coefficient which can be pulled outside the integral. That was a rule, by the way. So that way we can do just the power rule for an integral. Okay, so once we do that, we get 16 the integral of x to the 4th dx plus 24 the integral of x squared dx plus just have a 9 on the last one there. You can pull out that 9 outside as well. But basically, the constant in front just stays there, and we just take the integral of the power function, x to the 4th, which is x to the, we're going to add 1 to that 4. It's going to x to the 5th over 5, plus 24 x to the 3rd power over 3, plus 9x, plus your constant c. After that, you just clean it up as much as you can, simplify anything that you can simplify, and then that's your answer. Okay, here we have a couple more examples and with some trigonometric functions, but we're going to apply the same rules here, right? I can split the integrals here for each of these terms. We have that integral of sine of x minus cosine of x, minus 6 cosine of x dx. We can take the integral of sine of x dx minus the integral of 6 cosine of x dx. All right, looking at our basic integration rules, we have that the integral of sine is negative cosine of x minus, and again, that constant 6 I can pull outside the integral and just find the integral of cosine, and that is sine of x. Don't forget to add your c at the end. Okay, for the next one, I'm going to go ahead and distribute the secant to the other factor there, tangent x minus secant x. And I'm going to go ahead and split that integral again in those two terms. And I get to this integral of secant tangent respect of x minus the integral of secant square respect of x. And from our rules, we get that integral of secant tangent is just secant, integral of secant square is just tangent, and we add our c at the end. A couple more examples here with exponential functions. We have our integral of e to the x minus x with respect to x. Again, I split. Eventually, you can stop right in this step of splitting the integral. It's going to become more and more obvious as you do more of these. You can just go straight to the answers. Integral of e to the x is just e to the x, and integral of x is just x squared over 2. And then plus c. And same way, on the last example here, we have the integral of 4 over x dx plus the integral of secant squared of x dx. I can pull out the 4 outside the integral, since it's just a constant, and I have the integral of 1 over x dx. And the integral of secant squared, we've done it already on the example above. It's just tangent x. And from our rules, we know that the integral of 1 over x is just ln of x. And technically, I should have had that absolute value there, but there's our answer, 4 ln x plus tangent of x plus c. There you have it.